Hello, good morning, everyone. I'm really sorry that I could not attend the meeting synchronously online this morning. So I'm recording this as a recorded lecture. You can watch it at your own time. So what we have today is we are going to finish up simple harmonic oscillation, and then we will start a little bit introduction into talking about fluids. And Wednesday and Friday, we will finish our discussion on fluids. Okay, so going back to simple harmonic oscillation, in our previous class, we had talked about to analyze these two different cases, these pendulums, where case one is simply a stick pendulum, case two is a stick and a mass mounted together. So we figured out case one had a longer period by looking at it qualitatively. Okay, so we looked at for a stick pendulum and versus a simple pendulum. And case two is these two combined together. So the omega of that is within in between. So case one still had the biggest pendulum. If we wanted to work it out in more detail, we can calculate the exact period using our mathematical equations. So the angular frequency omega is square root of mass times g times the radius toward at the center of the mass. So this r is the distance from your center of the mass to your axis of rotation. So that's r divided by I, rotational inertia. So we can calculate the omega in case one and in case two. For case one, mass for the stick is simply just m, and the distance from the center of the mass of the object to the rotational axis is L over 2, half of the length. Okay, so that is for case one. Now, case two, you have a stick with mass m, you have a point particle with the same mass, so there are two masses, so it's 2m. And in terms of the distance, they all have the same distance, right? This point particle is the center of the mass, is where the point is, and the stick is at the same location. So the center of the mass of the entire object is still at L over 2 away from the rotational axis. That's how we expand the numerator for case two. In terms of the rotational inertia for these two cases, the rotational inertia for a stick is 1/3 ml squared. Now, this is relative to, they're rotating relative to one end. It's not rotating relative to the center of the mass. Okay, so this we had calculated for a stick. If you're rotating relative to the center, the I, center of the mass is 1/12 ml squared. But if you rotate toward one end, we had said using the parallel axis theorem, you simply add the original I onto n times distance between these two axes, which is L over 2 squared. So overall, they become 1/3 ml squared. So we're going to use this for the I, for the case one. For case two, the I would be the stick plus the mass. The stick is already calculated 1/3 ml squared. And the mass would just be a point. So that's mr squared, m L over 2 squared, given that this distance is L over 2. So the rotational inertia for the entire object in case two is 7/12 ml squared. So given that, you can plug in these specific numbers into your equation for a physical pendulum for omega. So omega in case one is square root of g over 2/3L. And in case two, the omega is square root of g divided by 7/12 times L. And we can just write this using g over This is 8 over 12 times L. So this is bigger than case 2. So the denominator is bigger in case 1, make omega smaller in case 1. And period is 2 pi over omega. So T1 is larger than T2. Okay, and you can calculate exactly what the omega and what the period is for these specific cases. All right, so that was what we have left off from our previous class. Just wanted to explain again the small angle approximation when we derived the equations of motion for pendulum. We derived the angular position theta as a function of time follows a sinusoidal function. In the small angle approximation, you can view this by looking at the Taylor expansion for sine theta, right? Sine theta is equal to this entire expression on the right. So when theta is small, then you can see theta to the power of third to the power of 3. All of these are higher order terms and is very small and can be neglected. You only need to keep the first order. So sine theta is approximately equal to theta when the angle is small. Okay, so that's why we could replace sine theta using theta in our equations of motion. We had the differential equation first, right, over here, and then we wrote down the solution to this, which gave us the sinusoidal solution. Let's look at one more question as a last question for this topic. Here we again have a pendulum, but noticing that our actual pendulum, physical pendulum, can be of all kind of different shapes. We had looked at a stick pendulum, but it doesn't have to be stick. For example, this pendulum looks like it's a loop. And you can still making it rotate back and forth like a pendulum. And so it's hanging over here over small nail, and that is the rotational axis, and it's going back and forth. So we wanted to calculate the angular frequency of this loop. Again, this is for small displacements because the solution we derived only were small angles. Okay, so this is just the assumption that is needed for the scale to be a good sinusoidal function. All right, so what is the angular frequency? So we have just calculated the omega, right, in the previous class, in the previous slide. That is mgr over I. Right, so we can still use that same expression here. All we need to do is to plug in the relative variables. What is m? M is just the mass. What is r? R is the distance from your center of the mass to your axis of rotation, and I is your rotational inertia. Do we know all of these terms? First, let's look at R. R is here right at the center. And the distance from the center of the mass to this axis of rotation is R, radius R, right? So that's just R. And rotational inertia, here we're looking at a hoop. Do you know the rotational inertia of the hoop? We do, right? For a hoop is really all the masses are concentrated at the same distance. So it's really just the sum of all the masses times r squared. So it's the total mass of the hoop times r squared. But remember, that is relative to the center of the mass. So if you're rotating relative to the center of the mass axis, then it is mr squared. But now it's rotating relative to one end right here, just like the stick. So we need to use parallel axis theorem to add the m times the distance between these two axes, and it is r. So it turned out we need to use 2mr squared for the I. Okay. Now we can plug in, sorry, g does not cancel. And you can calculate this is going to be G over 2R. In this case, 2R is simply your diameter, D. Okay? So the answer is A. You see that the shape can change, but if you go to this original formula we calculated and plug in the relevant terms, you will always be able to solve it. Right, so that's all we have for simple harmonic oscillation. The last topic of the semester is fluids. Okay, so we will start a little bit discussion of fluids today, and we'll finish it off for the rest of this week. Okay, so let's change our view to fluids. Oops. Okay. Okay. All right. So there are fluids. We will start with our discussion about static fluids. So static fluids simply meaning that fluids are not moving. And we will move on to talking about moving fluids. So fluid statistics and the fluid dynamics later. So you have already, with that lab we already did, I'm sure that you're already familiar with some of these concepts. The first thing we want to define is density, density of the fluids. So what is density? Density is defined to be the mass of an object divided by the volume of that object. You can see that if you have some metal, right? And then you could cut a small part of that, versus if you cut a big chunk of it, as your volume increase, you are getting more mass, right? So if you use that mass divided by the volume, you realize you get a constant. So if your mass doubles, then your volume doubles as well, give you that same ratio. And that ratio is density. This density is an intrinsic property of the material, meaning that if as long as you have your material fixed, then your density is fixed. It doesn't matter if you're trying to measure your density using a small piece of the material or if you're using a big piece of the material, because you're still using the same material. Your mass could change, your volume could change, but your density would not change. So we use m over v to calculate it, and we give it a Greek letter rho to represent density. Rho is m over v. The units we have for density, oftentimes there are two different kind of units. We either use all the kilograms per meters cubed for our density, or we use grams per centimeter cubed. So it's that kind of combination. So it's not we use kilograms per centimeter cube. So we usually don't mix them like that. Okay, so an example is the density of the water. Density of the water should be easy to remember, because if you're using grams per centimeter cubed, then the density of the water is 1 grams per centimeter cube. That simply means that if you take 1 centimeter cube, that amount of water, and then you and the mass, you measure the mass, it's 1 gram. That's it. That's all it means. If you're using kilograms per meter cube, what do you get? You get 1,000 kilograms per meter cube for the density of the water. Okay, you can see that 1 kilograms is 1,000 grams, but 1 meter cube is not 100 centimeter cube, because it's that dimension to the power of 3. 1 meter is 100 centimeters, but with the power of 3, you get 100 to the power of 3, you get 1,000,000. So you get 1,000,000 centimeter cubed. That's contained in 1 meter cube. Okay, so that's why 1 kilograms per centimeter cube for the density of water is 1,000 kilograms per meter cubed. So just be a little bit careful of that convention, of that notation of the units. Now, when we talk about fluids in our daily language, we simply referring to something we can drink, right? But in physics or in engineering, when we say fluids, anything that could flow, that could move, it's not rigid. So both air and liquid are what we study as fluids. So it can be air, it could be liquid. So for air, we have a bunch of molecules flying about, occasionally colliding with other molecules on the walls of a container. Why they are fluids? Because they are not rigid, is because there are a lot of space between these molecules. So for example, a gas can be compressed. You can squeeze a gas, but it's very hard to squeeze a solid object. The same way goes for a liquid. Liquid is fluids because it's easy to flow. But the difference between liquid and gas molecules and air is that for a liquid, the molecules are much closer together. So, so that it's not easily compressible like the gas, but it can still easily to be sliding around, to flowing around. So in that perspective, that both air and liquid can move around, so we consider them to be fluids as opposed to solid objects. Okay. There is another physics quantity we want to define. So we had density. Now we are talking about pressure. Again, we are familiar with the colloquial language of using pressure, right? So if you press on something, you can say, I'm applying pressure. So you probably already realized, okay, pressure seems to be related to the force. If you push harder, you're applying a bigger pressure, right? What other things could pressure be related to? Now, the pressure is also related to the surface area that you're applying that force. Like the needle, right? The needle is so pointy and so sharp, even a little bit force could make a lot of pressure. It's easy for it to puncture. But if you have a board, a very big surface area, and then it can help distribute and have smaller pressure. You have seen, probably have seen some of the performance people put on, like an acrobat kind of performance where they put a wooden board on someone's chest, and then they could put a big rock on the chest on top of the wooden board, and they would even pound on the rock, right? So the trick is that yes, that generated a lot of force, but they also using the wooden board as much bigger area to decrease the pressure, so make it still doable. But that's still, even it's more doable than just putting the rock directly on human's body and hammer on it. It still has to be with trained performer. So we obviously shouldn't be doing this by ourselves. But I just want to show that pressure depends on F and the area. But we feel pressure a lot in our daily life. Underwater, you feel the pressure. You can feel it in your eardrums. And when we are sitting in the airplane, when the plane, especially when it's taking off or landing, or when plane change its height, altitude, we feel that pressure in our eardrums. Because as you go higher in the air, you're moving to an atmosphere where it's less pressure. So you have this imbalance in your eardrums. So take a little bit of time to adjust. So you sometimes feel it. You hear about in our weather reports, right? They report about atmosphere pressure. And sometimes when you have a low pressure, of a day that make you feel a little bit uncomfortable. Obviously, we need pressures in our tires, in the cars or bicycles. So we need it to be at an appropriate pressure. We can also see pressure when you sometimes have punching holes in the can, if there's water in it, and you can see these little fountain lines. That pressure is the one that's forcing the water out of the holes. If we're talking about fluids, for example, the fluid exert a force on the surroundings, on the walls of the container. The pressure is defined to be that amount of force divided by the amount of contact area, so F over A. Okay, so that is our pressure. Pressure is, interestingly, even though force is a vector, when we talk about pressure, it's a scalar. Okay, it only has a number, but we don't talk about the direction of the pressure. The force, this force is a force that is perpendicular to the area. Okay, so when we calculate the pressure, if you can apply the force at the angle, but we only use the perpendicular force divided by the area to calculate our pressure. The units for pressure is, you can see simply, is newtons over meters squared, because the units for force is newtons and the force for the area is meters squared. So 1 Newton over a meter squared, we give it a new name called a Pascal. 1 Pascal is 1 Newton per meter squared. Likewise, you feel pressure in the gas, even though maybe that's less noticeable. If you put an object, any object that is surrounded by gas molecules are constantly feeling that force, feeling that pressure on the walls. The more area the object has, the more collisions that these gas molecules will be collide with the wall, and the more the force it will feel. And obviously force, if pressure is defined to be force over area, then force is pressure times the area. It's not just the wall. So right now we are in the room. You have air molecules around you, have air around you, the gas molecules. So they're pushing on your four walls. At the same time, they're applying a pressure on all of us. They're applying a pressure on all of the objects right now, like your table, like your laptop right now is feeling that force, that pressure from the air molecules around it. And you can use this classical view of how the pressure came out is these little molecules, they move and they collide, they bump into things, so that when they pound on your object, it creates a force. So that is where the pressure comes from. Okay. So usually most of the time you're surrounded by air, so they pound on you from all different directions. Taking this little cube, for example, the cubicle has the top and the bottom side, the front and the back side, and left and right side, right? So each of the side will feel pressure on it. So top pressure this way, bottom pressure this way, to the left pressure, to the right pressure. So eventually the total force is zero, right? That's why you don't see that the object's being pushed around and moving inside the air. There is no net force. However, the pressure is still very much there. Our atmosphere, we're living on Earth, our atmosphere at sea level has a certain amount of pressure, and we call it 1 ATM, 1 atmosphere pressure. That is equal to 101,300 Pascal. Okay, so that much pressure is what we experience on Earth at sea level. That's 1 atmosphere pressure. This pressure changes when you go up higher or lower. So if you go up in the mountains, you will feel smaller pressure because the air will get less dense. So you will not get at 1 atm, you will get a little bit less. But at sea level is 101,300 Pascal. So let's take a look at some of these calculations more quantitatively. First, let's look at the pressure inside a liquid. So here I have simply a container filled with water. Okay. Artificially, I separated a column of water with height D and a cross section of A. Of course, that you can't really separate this, right? But just imagine a column of water with that much depth and that much area. Okay, so we want to do a force analysis on this column of water. First of all, we're going to see, okay, let's just take the bottom layer of that column and see, okay, how many force is acting on it, the bottom layer. Right away, and you think of gravity. Yes, so there's the gravity, and this is we're just drawing the forces on the bottom layer, right? But it's for that entire column. So that entire weight of water from this column of water will be the gravity, will be the mg. But other than that, you can see there is this column of water is in contact with the air. So atmosphere constantly is pushing on anything that is in contact with. So atmosphere is pushing down on this column of water, right? So how much force is that? We know the atmosphere pressure has a pressure P, that's 1 atm. How do you convert that to force? So force is pressure times area. So if you're looking at a particular cross section of A, then that force is going to be P naught times A. So that is the force from the atmosphere. You have your gravity as well. Okay, both of these are pushing down, right? Gravity going down, atmosphere pushing down. But obviously our column water is not dropping. It's at static equilibrium. So there must be a force pointing upward. Okay, now this is from our pressure underwater. So you're above, if you're just on top of water, you have only atmosphere pressure. But if you went underwater, you also get the pressure from underwater, from the liquid. So there is a surroundings of this column water with all the other water surrounding it. These generate a pressure. So at the bottom surface, the water, so this is my column. This is my column. The bottom surface will feel the underwater pressure pointing upwards. Okay, so that is another force, that is P times area A. So P is the pressure at that depth times the area, you get a force upward. From this setup, we can calculate exactly how much pressure there is at a particular depth underwater. So these three forces cancel each other. So PA is equal to P naught A times the weight of this column. So the weight of the water is the density of the water rho times so we need mass times G. Okay, so mass will be density times volume. Volume is area times depth, A times D times G. So overall, the weight mg is rho A D G. So that's the second term over there. So we can cancel the A and we get P is equal to P naught plus rho times G times D. So this is hydrostatic pressure. You will feel that pressure when you're below a certain distance D away from the surface of the water. The deeper you go, the more of a pressure there is underwater. Okay, that's why when people go underwater, you want to be a little bit careful because the more deeper that you go, there's more pressure on you, and there is only so deep you can go to still for that to be safe. Okay, so let's take a look at this question you should have already done. Okay, so here we are looking at a container. Here's a very large pool, and we have a yacht floating on it. Directly under the boat, there is a point A, and somewhere in the open water, at the same depth down, there's a point B. So we wanted to look at the water pressure at point A and B. So one of the idea people may have is, well, I'm under the boat. Wouldn't that somehow affect my pressure under A? But look at this container, this is all connected. The point A and B, what they have in common is they're all under the same depth above the surface. So both of the A and B will have the pressure that is P naught, the atmosphere, plus rho times G times H. Okay, the H would be the height. They have the same height underneath, they will have the same pressure. So B is correct. So does the weight of the boat affect anything? Well, it simply does. Now imagine you have these 2 points and you don't have the boat, okay? Have the same pressure. And then you put the boat in, you add the boat. So what is the consequence of adding the boat? The boat, you can add the boat on top of a particular location, but because of the boat, it causes the water level to all rise at all places, okay? So now A and B, compared to when there wasn't a boat, A and B are now at a deeper distance away from the surface of the water, because now you add a boat, the water level rises. Okay, so that affected both A and B at the same time. Then all you care is whether they have the same depth, and if they do, they have the same pressure. So we're talking about the air molecules exert pressure, and even though we don't usually feel it unless we are, like we said, on the airplane, we feel that air pressure difference. We don't really even notice it's there, but it's there. The air molecule exert pressure on us right now. Most of the time we don't feel it because there's also air inside our body, okay? If there's only pressure from the outside but not from the inside, that will cause deep trouble. But because we have both air inside and outside, we don't really notice much of a difference. We don't even notice it's there. Now let's get an idea how big that pressure is. The PATM 1 atmosphere pressure is roughly 1 times 10 to the power of 5 Newton per meter squared. And we said it's 101, about 101,000 Pascal at sea level. So we just say, well, okay, roughly 10 to the power of 5. And if you convert that to pounds per inch square, and that's 14.7 pounds per inch square. So think about your surface area of your body. Every inch square of your body surface, you feel a 14.7 pounds pressure coming from the atmosphere. Okay, so let's take a look at a sample, an idea. If you're looking at, okay, if we take a spherical ball with a sphere with a radius of 0.1 meters, how much of that pressure, how much of that force is going to be? So we can calculate the surface area, we can calculate the force, we're using that pressure times the surface area, and we get 12,500 newtons. That's over 2,500 pounds. That's a lot of force, okay? So in history, people have demonstrated the powerful atmosphere pressure by performing an experiment, Magdeburg hemisphere experiment. Because a lot of times, right, if you have a sphere, but if you have air inside and outside, well, you usually don't see much of a difference. But if you could make air only acting from one side, let's say from the outside, and inside no air, then this much force pushing in is going to be really hard for you to separate the two hemispheres, right? Okay, so let's take a look at this demo. All right, so give me 1 second. I will change our view to the demo. Okay. This is a much smaller version of the experiment. In the actual experiment, one of the people have repeated several times. They used a bigger sphere, two bigger hemisphere, and they can put 12 horses to try to pull it apart, and they couldn't because they're too strong of the force pushing in. So what they're trying to do right now is to suck out the air from the inside to create a vacuum. Okay? They're trying to suck out the air from the inside the hemisphere, and they create a vacuum. And they close the valve so air cannot get in. Okay? And they detach the tube. Now you can see the air is pushing from all around, and they can no longer pull it apart. So 2 people. Add 2 more people, or maybe 20 people, probably won't be able to pull it apart because we just calculated it's over 2,500 pounds of force acting on the metal. So now they're just opening the valve, give a little bit of air in, and it's easily open up. Okay. All right. So this experiment just demonstrated just how strong the atmosphere pressure is, even though we don't even notice it's there in our daily lives. But like I said previously, if air is only pushing in from one side, we are in deep trouble. So let's take a look at this question. So we're looking at a big can, okay, with a radius of 12 inches at the top and bottom surface with a height of 34 inches. So this is in the shape of a cylinder. So what happens, what do you think will happen when air is evacuated from this can? I'll give you a moment to think about this. So we're able to create a vacuum. And once we create a vacuum, what do you think will happen? Do you think nothing happens? You just have a can that has the vacuum inside? Or would it be squashed like you're stepping on a soda can? Or would it explode? Or would it implode from all sides? So let's use the English units for this exercise. The 1 atmosphere pressure is 14.7 pounds per inch square. Okay, so just PSI, pounds per inch square. And we can calculate just how much force is on the top surface due to this atmosphere pressure. Okay, so if the top surface feel pressure, the force from the atmosphere pushing down, the bottom surface will feel the pressure pushing up because this pressure is from all around, okay? And the force is the pressure times the surface area, and we calculate that to be 6,600 pounds. That's a lot of pressure. So you can see that if there is air inside that can, then take the top surface, you have air molecules pounding from the outside, pushing down, but you have air molecule underneath it pounding, pushing up, and that balance out, so nothing happens. But if the air molecules is removed from the inside, you only get this air from the outside pushing down, right? So it certainly will be squished, but would it be squished just top and bottom, or would it be squished from the side as well? We said that air molecules are constantly acting from all around because it's collision is coming from all directions. So the side will feel the air molecules from the 2 sides as well. So if you remove and create a vacuum, then your gallon gallon drum, the cylinder will implode from all sides and get squished from all sides. Okay, so we will stop here today, and our Wednesday and Friday's class will continue to talk about how to calculate pressure, and we will also look at Archimedes principle. Well, that is one we did a little bit of that in the lab, so it would not be unfamiliar. We'll look at fluid dynamics. When you have air or liquids flowing, what can we calculate? All right, so that's all I have for today. I will see you guys on Wednesday. Bye-bye, everyone.